But the one thing I love about Pete, I think you can tell, is from his bio. The length of the bio tells me a lot about an individual. What I'm trying to say down here is Pete's been a remarkable person, and he's, if you look outside in the industry, Pete's seen very much as the father of TinyML. Of course, it's always, a team, community of people, but it's often, believe it or not, in the real world, you'll think, wow, how are all these industries getting created and so forth. But as you kind of mature and you see, there are few people who kind of really pull things in certain directions. It's remarkable that the entire field ends up moving that way, be it in processor, be it in software, be it in any particular theme or project you're looking at. It doesn't matter what the industry is. And I'd say like Pete is definitely sort of the head person for driving TinyML, especially on the software side. And obviously, Evgeny was there with us right at the beginning. And along with that, there are a handful of other key people that Pete's been instrumental. If you look up stuff, people in articles and so forth, people will often refer to Pete on the TinyML space. So Pete doesn't say much about himself, as always. That's the one thing I've learned about him, and it's also what I love about him. He's very humble. That said, Pete does a remarkable job in identifying like critical, interesting areas, and I think what he focuses on most is sort of like, very bottom-up approach and like actually doing stuff rather than just talking about, oh, we're going to have this exciting space. And I think like TensorFlow Lite Micro is that classic instantiation of moving the whole industry forward, but by kind of having some sort of mechanism on which the industry can actually build, right? Pete's written some remarkable number of blogs. I've always been a fan of reading his blogs. If you actually look at quantization on the things that we all take for granted today, you should look at the dates as when those articles were actually written. They date back quite a while. Pete, I can't do justice in talking about Jetpack, so maybe you can chime a little bit about Jetpack and also just a little bit of about how you got into the space and so forth before we switch into the technical aspects.
Yeah, and I've actually added a few slides as well with some photos from the Jetpack days at Drive request.
Maybe I'll stop sharing now. I'll let you kind of jump in slides and drive it.
Yeah. Well, I'm gonna get to. I want to keep people on the edge of their seats, so I'm gonna get to the Jetpack, the Jetpack days. But first, let's go back in time, and let me just. And you should see also in the chat that I've shared a link to these slides in case there are any URLs or anything that you want to. You don't have to try and scribble them down. You should be able to just use a link to the slides. So hopefully, try this again. Give it a minute or two. Can everybody see the slides?
Yep.
Awesome. And I'm not going to be able to see the chat, so just unmute yourselves and jump in if you have questions. Like I actually want to, as Vijay was saying, I want to have as many questions as possible. So, and really what I'm going to be trying to do in this talk is not rehash what's already in the paper, because I'm hoping you've had a chance to look through that already. Instead, what I want to do is sort of talk about some of the things that didn't make it into the paper and some of the sort of story behind how TF Lite Micro sort of came to be, because it's a very different story than you might see in kind of a dry academic sort of outline of we took these technical decisions and this is how things emerged. It was much more of a kind of accidental and conditional process that led to this. So I'm going to be talking about some of the ways that Micro came into being, and some of its sort of the background story to all of this. And to start with, the thing that might be hard to understand from the current perspective, where deep learning just seems to be everywhere and doing everything, and has solved AlphaGo and solved all of these really hard problems was that it was not something that people had really heard of 10 years ago. And especially Alex Krzyzewski's ConvNet paper back in 2012 was an amazing moment for a lot of people. And it really marked the point in my mind where especially computer vision started working. Computer vision was very, very hard to use, except in very specialized cases. And it took a massive amount of investment to get anything working. And so Alex came in with this paper together with, Ilya, and really showed that you could do an incredibly better job than previous techniques on this ImageNet. Hey, I've got to classify 1,000 different categories of images problem. And what is not often acknowledged is that it wasn't just a paper that was focused on, hey, here's this nifty idea. It was actually a paper that said, hey, I've got this nifty idea, and in order to evaluate it, I actually had to build it. And I had to build the end-to-end system. I not only had to sort of design the model architecture, I actually he had to write the software to train the model that he was building. And you can actually find his, it's been sort of archived now because code.google.com kind of got deprecated. But you can actually go and find the code still sitting out on the web with sort of 2011 last modified dates on most of it. And what was important here was that Alex's one of the real breakthroughs, there were several breakthroughs with this paper, but one of them was the fact that he was using GPUs to accelerate this deep learning work. And believe it or not, sort of back then, that was not something that people were really thinking about. But what that meant was that not only was he writing kind of training control code in Python, but he had to go in and write hand-coded CUDA kernels to actually implement things like convolution. And this was really important because even using things like NumPy, which had C++ code to accelerate certain operations, there wasn't anything that could execute the computations on the CPU that you needed on that sort of era of computer on the CPU. And in order to just figure out how to even train network architecture, he needed to try a bunch of different options and try a bunch of different sort of architectures, a bunch of different hyperparameters. And if training a single network would take months, then he would just run out of time before he was actually able to try a significant number of these different options. So by using an NVIDIA GPU and reducing the time it took to train down to a few days, he was actually able to experiment and really prove out the ideas behind the paper. But that meant that he had to actually write the inner loops of his ops in CUDA, NVIDIA's specialized version of C++. So really what I'm trying to get across here is that he's not only operating at this level of like, hey, I'm going to be inventing this sort of architecture and this approach and incorporating ideas like dropout and some of these sort of very high level sort of advances, he's actually also sort of really down in the weeds and messing around with very, very low level optimizations using things like CUDA. And if you want to check out the code, I've got a link here. And I have to say, I was blown away when I first started looking at this code, because I'm used to research code. You know, I'm a bit snobbish as a professional software engineer, and I'm used to researchers kind of creating code that's you know, fairly messy and undocumented and sort of suboptimal and just good enough to do whatever it is they need to do. And when I went in and looked at the code that Alex had been writing, it blew me away in how optimized, documented, and just generally how much work he clearly put in to this kind of code. And you can see I've got just a little extract of some of what he's doing here. As I'll explain later on, I spent a lot of time actually sort of going through and figuring out what he was doing for a lot of these ops. And I was really pretty blown away by the complexity of what he'd actually built here. And I don't feel like he gets enough credit for what he actually did on the software engineering side in this paper, as well as in the you know, sort of the machine learning theory side. So that's where I come in. It was around the time that Alex first started showing, you know, these amazing results. And I was the sort of CTO and founder of Jetpack, which was a phone app company that was running computer vision across lots and lots and lots of images from Facebook and from Instagram and from other sort of public sources of images, to try and build something that was a bit like Yelp, but based on photos of hotels, restaurants, bars, and other places people might want to go. And Brian asked for more photos, especially showing the people who are in the team. So this is the core of the team here, with you might see me in the bottom left and my co-founder Julian in the top right. And this is when we were on a trip to Vegas. So we were living back when we could still travel. We were, you know, trying to be travelers ourselves, as well as just building travel apps. And what we were doing was, as I mentioned, this idea of Yelp, where you have an app that takes all of these billions of photos that people are putting out on the web of themselves at different places, and actually trying to use computer vision, especially, to come up with lists for, I think we had 8,000 different cities around the world that we were able to automatically generate these sort of recommendation lists for. And, you know, the sort of things we were doing were, you know, the bars with a view and the scenic hikes were all about, hey, can we identify photos that were taken outdoors, but that were actually tagged at, you know, particular bars? Because then we could figure out, okay, if there are a lot of photos that were taken outdoors, but were actually taken at a bar, then we know that that bar has like outdoor seating, and we can identify bars with a view. You know, the same thing with looking at the trails where people took the most kind of outdoor photos. and also just looking at overall popularity and the number of photos that people actually took.
Pete, can I ask you, you're saying computer vision, so I'm curious. So when you say computer vision, at that point, were you all actually using computer vision-based methods, which we do today, or was it based on the tagging that was provided and then inference?
So we were actually using computer vision, but it was actually a lot of the approaches were very old school. So, for this, trying to tell if photos were taken outdoors, I hand wrote an algorithm that looked in the top third of photos and tried to tell if there were lots of pixels with a certain shade of blue, certain RGB values between sort of, one shade of blue and another shade of blue. And if there were, then I said, well, that's probably blue sky. So that was very much like a traditional algorithm, not using deep learning. And it was okay, but it was good enough, especially because we were running statistics across thousands of photos for each place. But it wasn't working great. And then, one of the things we wanted to do was, especially back in the early 2010s, if you wanted to identify where hipsters hung out in bars, like looking for mustaches was actually a good way of doing things. And the same for, we wanted to identify places where people could feel comfortable taking their dogs. And so we needed to identify dogs in photos. And that sort of algorithm, very traditional manual algorithm that we used for blue skies was just not going to work for those. It was not a practical approach. But that was right when Alex's work came out. And thanks to the fact that Alex had actually made the code open source, I was actually able to train networks to do some of the classification tasks like mustaches or dogs that I needed to do using Alex's software I actually had a machine at home that I used to have to babysit. Joanne, my wife, still remembers me. I would be sitting on the couch. We'd be sitting on the couch watching TV, and there would be this GPU plugged in next to the couch on the floor. And like every 20 minutes or so, I'd be sort of like leaning over and checking the loss function to make sure that it hadn't like veered off into some some crazy results, because I had to keep, it was so like delicate a process that I had to kind of keep hand holding the device whenever it was running to make sure that it actually kept working. And it was very loud and it was very noisy, and it actually worked quite well as a heater in the winter because it was like 1,000 watts or something of power that it was dissipating. And that was, and the other funny thing as well was the only way back then that I could get a machine with a good GPU kind of pre-installed was to buy a gaming machine. So I ended up with this machine that was had like glowing neon internals because that was the only way that you could actually get pre-built machines with high-end GPUs. They assumed you were using them for gaming. So I had this, I felt like a 14-year-old kind of with too much money, with this crazy sort of gaming thing sitting next to me on my couch. And so the cost for that was about $5,000. And I had to sort of estimate this, back from my memory, but, I believe, we could probably process maybe 100,000 images a day with that machine. But we had billions of photos that we needed to deal with. And it was going to be really hard to spend the amount of money that we needed to buy enough machines to get through billions of photos on our, we'd raised a few $1 million, but that had to last us for salaries, for, and everything else that you needed to do around building an app. And even on AWS, for cloud machines, you'd still be paying sort of double-digit dollars a day for a GPU machine, because again, back at that point in sort of 2012, 2013, the only reason for using a GPU machine was to do some crazy sort of gaming, streaming sort of service. And the overall cost worked out to be, only a fraction of a cent. But that sort of, 0.02 cents per photo still meant that dealing with 1 billion photos, we had several billion photos from public Instagram sources and things like that would cost us about $200,000 on these GPU machines. And we couldn't afford that. We were going to run out of money if we had to spend that much to run computer vision across these machines using Alex's CUDA ConvNet. But one of the things we realized was that
All right, Pete, Robert had a
question.
I was just waiting for you to finish the slide.
So getting back to the problem that we were facing, we needed to run these networks across billions of images. We couldn't afford to do it using GPUs. But what we realized was that training has to happen on a GPU because you really need low latency iterations on the weight updates. Like the whole time of training, you have to run a batch of images through and then change the weights based on the results and then run another batch of images through. It's very hard to do that. It's possible to do that distributed across multiple machines, but that's quite a big challenge. And especially back then, it was extremely hard to do. But the key bottleneck there is that you have to wait for the weights to change. But doing inference, you can do with fixed weights across a whole bunch of different machines. And it turned out that we could hire literally over 100 kind of middle to low end CPU only machines for the same price as one of those GPU machines. And while inference was taking a long time, would take a long time because the CPU machines don't have nearly the same amount of arithmetic capability as a GPU machine. So the latency for running one image would increase, but we didn't really care about the latency for an individual image. We cared about how many images per hour we could actually put through these devices. And having a network of 100, even if each individual machine could only manage 10% of the speed, we could get 10 times the number of images across a given time. And that really changed the economics so that we could afford to run several billion images through these models and only pay sort of, $10 or $20,000 per billion images, which made it a lot more affordable. The only problem, this is why I'm leading up to, what I ended up doing on TensorFlow and TensorFlow Lite Micro, is that there was no CPU path for CUDA ConvNet. And other implementations like Caffe were only just starting to emerge that had CPU paths. So in order to run on these CPU machines that we needed to use for economic reasons, I actually ended up writing and open sourcing my own inference-only framework that imported networks that you were trained in CUDA-ConvNet, but had optimized CPU implementations of the different operations. And this worked, and it let us run our moustache detectors across these billions of photos. And I highly recommend it as an exercise as well. If you ever get a chance to just write your own code to implement one of these, frameworks to run one of these networks, it's super educational and super interesting. As a byproduct of the way that I'd written it, it also turned out that writing something that was CPU only, that was fairly, dependency-free code, made it possible to port it to Android, iOS, and things like the Raspberry Pi. And what we noticed was that a lot of the people who were grabbing this code were having a lot of fun with it on these mobile platforms. And what really was the hardest part about writing this whole thing was that I wrote an exporter from CUDA-ConvNet that did what I needed for the particular networks that I was training. But people wanted to run all sorts of other networks from CUDA-ConvNet and from other networks like Caffe on mobile devices. But writing the exporter and extending it was really hard because there was this almost endless series of different ops that people had written. And again, this is coming back to this work that Alex originally had done, where he was like, hey, I have to speed up convolution. I have to speed up these ops that I'm running, so I'm going to be able to run my network in fast enough time. So I'm going to write a bunch of optimized code to implement these ops in a language like CUDA. And the problem that left for people down the line, like me, who are trying to implement different, take that network and get it running in a different environment, was you were left with this massive lump of optimized CUDA code, and you had to figure out, okay, how do I emulate that in this completely different framework, in this completely different environment? And people just kept on inventing more and more variations on different ops, and the only way they were defined was by this kind of optimized code. So that was around the point where Google came calling, and they were really interested in the technology that we'd put together, especially around running deep learning in very resource-constrained devices and sort of mobile devices. So we ended up joining Google. But to explain, because this is a recurring problem that's not as well understood as it should be, like how to port a new op was this very tricky multi-stage process. You have to figure out what the op's doing. You have to figure out how to create some unit tests for it. You have to rewrite the code. You then have to figure out if the code that you've rewritten is actually semantically equivalent to the original code by using unit tests and example networks. Then you have to optimize it again and make sure all the optimized code passes. And then you also have to deal with all of the edge cases where something you haven't thought of gets passed in as a parameter, and your code works differently to the original highly optimized code, and sort of figure out why that is happening. And if you imagine,
Tom's got a question.
Yeah. And yeah, that's a good background to this, this process where people kept following in Alex's footsteps, and they would write, researchers would come up with new ops, and they'd write optimized C++ and CUDA code to get them running and training, and then release the code in the paper. And every one of those ops, if you wanted to support them, you'd have to have somebody who was very conversant with both ML and sort of optimization and particular platforms go through this entire process for each one. And last time I checked, there were over 2,000 different op implementations in a network like TensorFlow, and other networks like PyTorch also have very large numbers of ops. And the process of porting these to different frameworks take a lot of skill and time, and they're extremely hard. So this is all sort of leading to the fact that there's this really big tension still in deep learning today, where researchers keep creating these complex new ops and then kind of releasing them as optimized code. But then people who need to run them on different devices, people who need to deploy them, have to somehow wrestle with all of these new ops and figure out which ones are important to get running on other platforms. And there have been a few different approaches to this. One of them is, hey, can we stop researchers writing this complex C++ and CUDA code and write in some other domain-specific language? And we haven't managed to do this yet. It's a nice idea. The problem is that it's still easier and makes more sense for researchers from their own incentives to just go ahead and do the straightforward thing for them, which is to just write the optimized code they need and then just move on to whatever's next. So that still leaves somebody, even if you've got an intermediate representation like MLIR, XLA, or Onyx or something like that, you still have to have somebody doing all of that manual work to take that optimized version and turn it into another representation. And the other thing you can do is just say, hey, let's take that, it's C++ code usually, let's just take that whole thing and run it on different platforms. And the trouble is that both PyTorch Mobile and the original TensorFlow Mobile took that approach, and they were just so large that it was very hard to fit into apps. And also just keeping all of the dependencies that people pulled in was extremely hard. So you might be wondering, why am I setting all this context? What has this got to do with TensorFlow Lite Micro? I saw over the last few years this growing demand for running machine learning on microcontrollers, but I'd worked on a whole bunch of projects where there had to be a translator exporter to take all of these ops that people had written in an optimized way and get them working in a different platform. I never wanted to kind of get involved in that, be on the hook for that again, because it was so hard to scale and it was really hard to just manage from the software side. So one of the things that we talk about a bit in the paper, but that I'm really sort of emphasizing in this talk, is that we decided to really try and leverage the existing exporting tooling for TensorFlow Lite and reuse that ecosystem so that honestly I could focus on the fun parts of trying to get the code running on tiny platforms. And this meant that a lot of what we're doing is a trade-off. It's not like the perfect representation, the serialization format, like some of the other design choices around TensorFlow Lite weren't things that we would necessarily have made if we were designing something from scratch. But really, this let us make progress. And, some of the drawbacks that you'll probably encounter when you're working with this is, this translation problem and the fact that we only support 55 out of, a potential 2,000 ops means it's easy to get yourself to a point where you've got a training side model that you can't actually run in micro. but this is actually something that's true for almost everything except frameworks that pull in the full optimized C++ implementation of all ops. So is this an important thing to worry about? As long as you're using a model that has been ensured that it's actually using supported ops, then you're fine. But it does mean that there's a cost to trying to do something really new or unique. And I also, as you're looking at the different inference solutions, because this applies to almost all of them, beyond TF Lite Micro, you have to be thinking about it when you're evaluating how well a framework is likely to work in practice for a large number of users. You can often create benchmarks that look good on a few models, but if the process of taking new models that you haven't thought about supporting is super onerous, then that's going to radically affect the experience of users of those systems. So the only way we're going to get past this is if we stop researchers writing new ops in this kind of messy, optimized form. But the only way that that's going to happen is that there's got to be a better solution, something that's better than writing in raw C++ or CUDA. And as deployers, we can't force this change because researchers usually outrank us. So until this, whatever new technology that helps make this magic world happen, and people aren't going down the Alex Krzyzewski route of having to be researchers who write ops in CUDA, we're going to be stuck in this world of incomplete translations. And this ties into the whole design theme of TF Lite Micro, where we really had to identify any bottlenecks that would prevent us from scaling. And this was a really important bottleneck, which is why I've spent so much time on it. But we really, the thing that I think worked best for us was that we were able to identify things that would just take up way too much time and block our progress, and find ways to design our way around them. Because it was me and Rocky working half-time, just a couple of years ago, as we were putting this together. So we didn't have any time to waste. I've talked already about translation from training. There were a few other bottlenecks I'm going to quickly go over. One of them was, porting dependencies, optimizing operations, and working with different build systems. And if we got stuck spending significant amounts of time on any of these, we would fail because they could just take up all of our time. And what we really needed to be able to contribute were things that other people couldn't. And these included like end-to-end example models and all of these things that are much more around specifications and what we've learned from product teams. And I've already talked about translation from TensorFlow from the training environment. Porting dependencies, because we really didn't want to get stuck into trying to figure out how to get different libraries running across these platforms. We avoided that by paring down the code to call almost no libraries. And we were fairly successful here. We don't even call things like malloc or operating system calls or printf. So that means we can port to almost anything that just has like a raw C++ compiler and run on bare metal. And we opted out of writing any optimized implementations of operations. We made it our job to create reference code and unit tests and benchmarks, and then try to make it really easy for vendors to plug in their own optimized operations, because there were dozens of different platforms that we needed to support, and there was no way that we could write all of those operations ourselves. So we sort of, ducked out of that work by making it as easy as possible for vendors to do it for us. And build systems take up an incredible amount of your time if you become a professional software engineer, and especially one that works across different platforms. So we really tried to keep the compilation process as simple as possible so that there were no fancy things you needed to do as part of a build system, and you could just drag and drop essentially your files into any different IDEs. And one thing that we've sort of touched on is a lot of people are using code generation, things like TVM, things like Glow, things like ST's CubeMX. So part of that is because we actually don't, there's a lot of kind of instinctual reaction to interpreters as being slow, because you're used to running interpreters on traditional kind of procedural code, and there they run a lot more slowly than compiled equivalents. Like Python versus C++. People wrote operator implementations in C++ because doing the heavy lifting in a compiled language was way more efficient and much lower latency than writing the same code in Python. But because each op in a machine learning network might be hundreds of thousands or millions of arithmetic instructions internally that execute, the fact that you're running an interpreter to call each op really doesn't have a major overhead. And that's, I think, VJ helped us collect some data in the paper that really shows, it's usually less than 1% of the compute cycles for reasonable sized models. And even with very small models, it's only up to sort of 4%. This is also something that I've kind of imposed on the project myself. I hate writing code to write code, if that makes sense. And I really find it way easier to make fast progress using kind of a traditional approach, where if you need to optimize something, you go in and actually change the code you want to optimize, rather than changing the code that generates that code that you want to optimize. So because I've been focused on making as fast progress as possible with as small kind of team as possible, having that extra step of interaction with code generation has just been something that I've been trying to avoid doing for as long as possible. I'm basically letting sort of benchmarks and the other hard metrics that we care about guide me. And I see code generation as something that we'll use as a tactic when we need to, but making progress without it is a lot easier for us. But I'm also recognize that this is something that a lot of other smart people who are doing great work disagree with. So this is just kind of very much a personal perspective on this. So that was kind of a whistle-stop tour of some of the things that I don't think we covered in much depth in the paper, but I thought might be interesting to you as people who are looking at this paper. I was hoping that people would sort of jump in and start grilling me on this or anything else that really came up when you...
Yeah, in the discussion, sorry, not in the Zoom, but in the Canvas discussion, there are loads of questions. So obviously, the paper has got a lot of questions, so maybe we can take this chance for you to ask questions.